Jungle. Transformer is a static electrical device used to transfer electrical energy. While the size and type of transformers may vary, the basic principle of operation is the same. To understand the functioning of transformers, we have to first understand electromagnetism. When some current is flowing through a conductor, magnetic field is produced around this conductor. If we turn this conductor into a loop of wire, the magnetic effect remains the same. We can add more loops to form a solenoid, which produces a stronger magnetic field. The magnetic field is steady because we are passing DC current in the coil. If we pass alternating current in the coil, the magnetic field will also change according to the polarity and magnitude of the current. If we introduce another coil near the first coil, the changing magnetic field from one coil produces electromotive force across the other coil. This creation of EMF in a conductor inside a changing magnetic field is known as electromagnetic induction. We can see that only few magnetic lines are linked with the coil and the rest are wasted. To concentrate all the magnetic lines, a ferromagnetic core is used in between the coils. When the number of turns in primary and secondary coils are the same, the EMF across them is also the same. Less turns in secondary coil reduces the output voltage. This type of transformer is known as step-down transformer. More turns increases the voltage. It is known as step-up transformer. Although this setup represents a single-phase transformer, the same idea is used in the construction of a three-phase transformer. Since the rating of these transformers is very high, the core requires thick insulation of pressed board. The primary coil is wound around this insulation. The coils are wound in spirals, forming separate discs connected to each other. Each disc is separated by using spacers. Some transformers use winding material which are already wrapped with thin sheets of insulating paper for better insulation. A pressed board wraps the primary winding around which the secondary coil is wound concentrically with the primary. Finally, the secondary winding is also wrapped with a pressed board. The input and output connections of single-phase transformer is straightforward and simple, but a three-phase transformer connection is quite tricky. Let's take the primary windings, for instance. There are two ways to connect these coils. One is called star configuration, in which all three similar ends are connected to form a common neutral, with remaining ends being phase terminals. Another method of connection is called delta connection, in which a starting of one coil is connected to the end of the other. No neutral point is obtained from this configuration. In the model shown here, the primary winding is connected in delta configuration, and the secondary winding is connected in a star configuration. This type of connection is known as delta star configuration. We learnt that a metallic core is crucial in a transformer, but it also comes with some drawbacks. Whenever a changing magnetic field is passing through a metal, eddy current is developed perpendicular to the field. Eddy current causes loss of energy by opposing the available magnetic field. Since the eddy current flows about the cross-sectional area of material, reducing the area reduces the magnitude of the eddy current. This is why transformer cores are made up of thin insulated sheets instead of a solid metal. The core also bears hysteresis loss. When some magnetizing force is applied to a magnetic material, magnetic lines are developed within the medium. Let's observe this in the molecular form. When the magnetic field is not applied, the magnetic domains inside the medium are pointed in random directions. As the magnetic field is applied, the domains align to the direction of the applied field. The domains have to overcome some friction during the process, which causes wastage of energy, resulting in hysteresis loss. Some energy is also lost due to the internal resistance of the coil itself. All these energy losses produce heat inside the transformer. To combat this heat, the main tank of transformer is filled with insulating oil. Heat radiators are used in transformers to dissipate the heat. The radiator has multiple hollow fins, which spread the oil to a large surface area, thereby increasing the rate of heat dissipation. Large transformers utilize electric fans to cool the radiators. Above the roof of the transformer sits a conservator tank. This tank is partially filled with oil, and the remaining part is occupied by an air cell. When the temperature of oil increases, its volume also increases, which squeezes out air from the air cell. This displaced air enters the breather pipe. This pipe is connected to the breather through which the air escapes. Air also re-enters through this breather when the volume of oil decreases. Breather is filled with silica gel to absorb any moisture that may be present in the air entering the tank. Transformers are fitted with a gas detector known as Buchholz relay. It is responsible for disconnecting the main supply to the transformer if it suffers any major faults. An explosion vent is fitted on the roof of the transformer. It has a diaphragm which ruptures when pressure inside the transformer reaches certain levels and prevents explosion.